In this video, we'll be looking at alkene reactions and then its structure. Now, when we say alkenes are hydrocarbons with at least one double bond, and then they have a general formula of CnH2n, where N starts from 2 to infinity. So with alkenes, there is nothing like N equals 1. So bond, the least alkene compound you can talk about is ethene or ethylene. They are the same. Now, when you say alkenes have only at least one double bond, it means that you can have an alkene compound which has more than one double bond. In the case of a compound, let's say with 4 atoms with 2 double bonds, because of the 2 double bonds present, or even because of just one single bond, one double bond here, it makes it an alkene. And then because the double bonds are 2 here, it becomes a dialkene or diene. So if it is a butene but then it has 2 double bonds, then we call it butadiene. Means that it has 2 double bonds. That's why there is a diene present. Then just have to add your prefix, which is but, for 4 carbon atoms, making it butadiene. Now with the reactivity. And before we talk about the reactivity, let's look at the main structure of alkene. We said that alkenes have double bonds. So when I take an alkene compound like pentene, which is a 5 carbon atom with one double bond present, the rest are all single bond. In the case like this, because it's an alkene compound, all the carbon atoms present which have the double bonds are all sp2 hybridized. So if I label this as carbon 1, 2, carbon 3, 4, 5. So starting from carbon 1, here we are looking at the hybridization. So with carbon 1, when you look at the carbon atom, it's surrounded by a single bond only. So then it becomes sp3 hybridized. Then look at carbon 2. It has a double bond here, and then there's a single bond here. Whenever double bond and single bond meet, the double bonds presses the single bond. Now you can see that this carbon atom here has a double bond. Then because of the double bond, it becomes sp. This carbon atom too, the third carbon also has a double bond present attached to it. So it also becomes sp2 hybridized. And then this has only single bond present with sp3 hybridized. And this carbon is also surrounded by double single bonds only. Then it's also sp3 hybridized. Now with the bond angles, when it's sp2 hybridized, the bond angle is 120, and then the shape is a trigonal plane. And then when it's sp3 hybridized, the bond angle is 195 degrees, and the shape is a tetrahedral shape. So this is for hybridization. Now let's talk about the reactivity of. Now, because alkene is unsaturated because it has a double bond. And then with a double bond, we know that whenever you have more than one bond, actually a double or triple bond, it means that there is only one sigma bond present and the rest are pi bonds. Then we know that the pi bonds are the localized bonds which has localized electrons. So that makes it very reactive. So we can see that alkenes are unsaturated and that they undergo addition reaction. But then for alkenes, they are saturated, so it can't undergo addition reaction. It can only undergo substitution reaction. So taking the addition reactions of alkene. Addition reaction means that when you have any alkene molecule, let's say propene to C3H6, and I'm adding a different compound to it. So let's say hydrogen chloride. Now because this propene itself is unsaturated, it has double bond present, and then so we can add this hydrogen chloride to the alkene molecule to form one bond or to form one compound, and that's why we are saying it's an close addition. Now When talking about the addition reaction here, so let me split the compound. It's propene, so there's a double bond here. This hydrogen chloride here, it split or dissociates into a partial positive for the hydrogen, then a partial negative for the chlorine. So the hydrogen here, because we're doing addition reaction, the idea is to break the double bond present to make it single bond. So for every one double bond you have, we need two atoms of a compound, or let's say two atoms of an element to break that bond. So if it's a hydrogen, that means you need two atoms of hydrogen to break a one double bond. And then we have two elements here, which is similar to saying H2 here, two molecules of hydrogen. One hydrogen molecule will attack this, and then the chlorine has to attack the other one. So now how do we know that this chlorine should attack this particular bond, or it should attack this? Because when I have a compound like this, and I'm adding plus HCl, and I'm seeing that this hydrogen should attack this bond. That means I'm going to get CH, and then I'm seeing the chlorine should attack the second one here. So I'm going to get this H here going into this C here, and then the C is being attacked by the chlorine here, going to C. Now, when I name this compound, I'm going to get a different name as opposed to me saying that the chlorine here is rather attacking this. Now the hydrogen is now attacking this. So in that case, I'm going to get something like C bonded to Cl, going into another C bonded to H. When I name these two compounds, I'm going to get different names. So now, a man sat down to bring about a whole idea on how to go about this. And then the rule is called the Markovnikov rule. So the Markovnikov rule in simple terms states that hydrogen is added to the carbon with the most hydrogens, and halide is added to the carbon with the least hydrogen. So this is what it means. Or in other terms, you can say that whenever you want to break a double bond, you add the nucleophile. So the nucleophile refers to the electron weight species, which is the more negative electron, the more negative element or the more negative. So we add a more negative species, which is the nucleophile, to the carbocation. So the carbocation is when you have any compound and then we split it into the partial positive and partial negative. The carbon in the partial positive becomes a carbocation, and then the one in the partial negative becomes a carbanion. So with the Markovnikov, you are going to add the nucleophile, which is the most negative one, to the carbocation, because you know um, positive and negative attract. And then we are going to add the electrophile, which is the electron deficient or the positive species, to the carbanion. So in that case, that will give us the best product to be formed, or let's say the major product to be formed. Or in simple terms, you can just say that with the Markovnikov, we add hydrogen to the carbon with the most hydrogen, and a halide to the carbon with the least hydrogen. So when you have an alkene compound, so we have let me try propene. I'm adding HCl. Now this propene, this double bond has to be broken into the partial positive and partial negative. So how do you know that this carbon will rather take the positive, or this will rather take the negative, or this will rather take negative, or this will rather take positive? So the other rule is that the more stable carbon atom will have the partial positive, and then the least stable becomes the partial negative. And then to identify the more stable cation, so the more stable cation becomes the carbocation, and then the least stable becomes the carbanion. So to identify the more stable, which is the carbocation, you are supposed to look at the carbon which is more substituted. So the more substituted is refers to you having a carbon that has other compounds present aside hydrogen. So you look for the double bond present. The double bond is between this carbon one and then this carbon two. Now with this carbon one and this carbon two, which of them is more stable? You're going to look at the carbon which is which has more substituent. When I take this carbon, it's it's bonded to this carbon which is one substituent, bonded to another carbon here which is, so it has two substituent. But then when I take this carbon is bonded to only this directly which is one. So this carbon is di-substituted, but then this carbon is mono-substituted. Which one is more substituted? It's the di-substituted. So then this carbon becomes a carbocation. When I'm going to do the splitting, I'm going to do it in a way that we'll be getting C bonding to C partial positive, and then the double bond here goes to C partial negative. Now, hydrogen and chlorine, which one is more electronegative? Definitely it's chlorine. So chlorine is more electronegative. Then hydrogen is more electropositive. So hydrogen here becomes, this hydrogen here becomes our electrophile because it has a positive, and then this chlorine here becomes our nucleophile, and this becomes our electrophile. And then from the Markovnikov we said that the electrophile, which is the positive, should attach itself to the carbon with the negative or the carbon anion, this. And then the nucleophile will attach itself to the carbocation. Or in simple terms, like we said that the hydrogen will attach itself to the carbon with the more hydrogen. And then the halide, which is the chlorine here, will attach itself to the carbon with the least hydrogen. Now let's try both and see if we are going to get the same answers. Now this is our nucleophile. It has to attach to this carbon, which is the carbocation. So we get C bonding to C, then our chlorine here. And then this carbon, our carbon anion, is being attached to our electrophile, is being attached to our carbon anion. So we get C to hydrogen, and then we are getting this compound. Now when you try the simple way of expressing the Markovnikov, we state that the hydrogen is attached to the carbon with the more hydrogen. So in simple terms, we used to see that the rich gets richer and then the poor gets poorer. So in that sense, we are saying that the carbon with the more hydrogen becomes, the carbon with the more hydrogen will get the hydrogen, and the carbon with the least hydrogen will get the halide. So when you look at this compound, you can draw them and see the number of hydrogens. So this one has one, two hydrogen. This one has only one hydrogen. So it means that this hydrogen will attach to the carbon which has the more hydrogen, which will be here. And then the halide will attach the one with the least hydrogen, which will be here. And then remove our double bond here. So it becomes just one single bond. And then realize that it's the same as this. So anyway it is correct. It's either you use a simple method. Hydrogen goes to the carbon with the more hydrogen, then the halide goes to the carbon with the least hydrogen. So that's the whole concept about the Markovnikov. We have other, we have the anti-Markovnikov rule, which is the exact opposite of the Markovnikov rule. So with that one, the more hydrogen, the hydrogen goes to the carbon with the least um hydrogen, and then the halide goes to the carbon with the more hydrogen. In this instance, the anti-Markovnikov rule works only when there is um hydrogen peroxide reagent present. So anytime you see a reaction, let's say propene C3H6 plus let's say hydrogen fluoride, and then there is a reagent like hydrogen peroxide H2O2. So in this case, your major product that will be formed will be the anti-Markovnikov product, not the Markovnikov rule. So even though we apply the Markovnikov rule, you realize that you can form two different products for every addition reaction you do. The simple case we used with the propene one, we see going to C double bond C plus HCl. We can get our hydrogen being attached to this, and then sorry, we can have our hydrogen being attached to this carbon, even though this carbon has the least hydrogen. So when we are doing it this way, that means we are doing the anti-Markovnikov. And then we say that the halide will be attached to this carbon with the more hydrogen. So we are still doing the anti-Markovnikov. Or we can do the Markovnikov rule one, and that will give us the chlorine attaching itself to this carbon rather, and then the hydrogen attaching itself to this carbon rather. Now when you do this, you are going to get two different products, product one and product two. Now naming this different product, when you want to name this will simply be one chloropropane, and then this one will be two chloropropane. This compound will be two chloropropane. This one will be one chloropropane. So it means that when you react propane with hydrogen chloride, you are going to get two products, one chloropropane and two chloropropane. Now which one becomes your major product? Based on the Markovnikov's rule, the two chloropropane becomes our major product. So we can even write both products and then we indicate that the Markovnikov's rule is our major product, and then this is our minor product. It doesn't mean that the minor product wouldn't be formed. When you talk about reactions, you have something like side reactions. Then the side reactions is that the reaction that we want, which is the desired product we want, we might not get it always. So then we get something like our side product or undesired product, and that becomes our minor product here. So here we bring something like a yield. So we can see that when you react your propene with HCl, you're going to produce, let's say, 80% of two chloropropene, and they are going to produce like 20% of one chloropropene, but then the actual product that will be formed is two chloropropene. So that's all about the alkene reactivity and then the alkene structure. So the anti-Markovnikov is the exact opposite of the Markovnikov. Let's try one example of the Markovnikov rule and then we'll end it there. So we have a compound like C bonding to H going to C double bond H, and then this 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 4. Yes. When you are reacting this with hydrogen fluoride, you can pause the video and then try out and compare your answer to my own. Now this, we have to look at where the double bond is. The double bond is between this carbon atom and this carbon atom. Now, which of the carbon is more stable? So the more stable one is the carbon with the more substituents. So when I look at this carbon, let's say I'm calling this carbon 1 and this carbon 2. This carbon has two substituents, this part and then this part. So two substituents. This carbon has only one substituent, that is only this part. Mind you, hydrogen is not a substituent. So this carbon has two substituents and then this carbon has one substituent. And because this has two substituents, then this becomes our carbocation. So this becomes our plus, and this becomes our minus. We are going to get C to C to C plus, double bond C minus, to hydrogen plus. Now hydrogen and fluorine, which one is more electronegative? Fluorine is more electronegative. So H plus F minus. Our H plus here becomes our electrophile. So electrophile goes to our carbanion, and then our nucleophile goes to carbocation. We are going to get C bonding to C bonding to F, going to C bonding to H. So this becomes the product that will be formed, and this becomes our Markovnikov's product or our major product that will be formed. We can reverse it and then do the anti-Markovnikovs, where hydrogen will rather go to the carbocation, then fluorine will go to the carbanion, and that becomes your minor product in the sense that it's unlikely for this to occur. So let's say there is a 90% chance that this product will be formed, and there is just 10% chance that this one will be formed. Now let's look at one very last one. One very last one. Because in our previous examples, we realized that there's always one carbon atom being di-substituted whilst the other one was mono-substituted. So now let's look at a carbon compound like C double bond C to C here. Then let's say to C here. So now if you are adding this to hydrogen fluoride, what will be the major product here before? The major product here will be our Markovnikov's product. So these are double bond and these are the carbon atoms that we are looking at. This carbon is bonded to this and then this. Now this carbon is bonded to this and then this. So they are both di-substituted because this is bonded to one and the whole of this, and this is also bonded to this and the whole of this. So you have to count the number of carbon atoms. This one is bonded to a methyl group and then 1, 2, 3 methyl group. But then this carbon is bonded to two ethyl groups. So we have ethyl here. So this one is bonded to, this carbon atom is bonded to one methyl group and then a propyl group here. But then this carbon atom here is bonded to ethyl here and another ethyl here. Now which one becomes our carbocation? They are both di-substituted. Now let's look at the number of hydrogen present. I'm sure there will be the same number of hydrogen present. So we have 1, 2, 3, 4. 1, 2, 3, 1. Yes. So this particular carbon has just one hydrogen present. 1, 2, 3, 4. And this particular carbon has also one hydrogen present. But then you have to look at its substituents. So its substituents are this and this. Now because both are di-substituted, you are going to look for the product that will go with the Markovnikov's rule. But then because they are both di-substituted, it means that any of the products can be formed. So it's either hydrogen, this becomes a carbocation, or this becomes a carbocation, or this becomes a carbanion, this becomes a carbanion. So you can do it in two ways because they are both di-substituted and then the hydrogen atoms present on the two carbons are the same. Now in cases like this, so this becomes your final answer. You are going to get, so you first treat this carbon as a carbocation. You are going to get C bonding to C carbocation going into C carbanion to C, and then you have another one C, this being your carbanion going into C, this being your carbocation C, and then our hydrogen is H plus, our fluorine is F minus. So using the Markovnikov's rule, the hydrogen plus will have to go to this and then the fluorine will go to, you are going to get C going to C, going into CH, then C. Then this becomes one product. And then you can have your H plus going into your carbocation, your F going into carbanion. In this case, this is the anti-Markovnikov. You're going to get C going to CF. Yes, so yes, C going to CF, going to C, going to H, then C, then C. Did I do it right? This one has to come here. This one has to go here. Right. Yes, so for this part, this one has to come here. Yes, so we end up getting these two different products. It's coincident that they are the same, but then in a case that we have something like H here and then F here, yes, we're getting something like this. Because the two carbon atoms, they are both di-substituted with the same number of hydrogen, they are going to produce two products, both Markovnikov and the anti-Markovnikov. In such case, when you write your answer, you're supposed to write both products, and then you will see that the yield will be 50%, 50%, which means that there's a high chance of each of them forming. And then in a case where one was highly substituted than the other, then the Markovnikov's one becomes like 80% or 90%, while the anti-Markovnikov becomes 20%. So that will be all for now.